So this talk came out of my annual couldn't decide what I wanted to talk about thing. So what I did was I put out a vote on Facebook and gave about 4 or 5 different topics. And this is the topic that won out. It got a grand total of 8 votes. So when I found out, and let me get my special effect here, when I found out what I was going to be talking about, I did a little research, but I confined that research to the well-known, very authoritative realm of social media. Needless to say, I learned a lot of very interesting things. For instance, I learned that star is following me. I learned that planetary alignment is going to cause horrible earthquakes and we're all doomed. I learned that the Earth is flat and is surrounded by a giant circle of ice that no one has ever seen for some reason. I learned that Stanley Kubrick faked the moon landings back in 1969 in order for whatever reason. In fact, I learned that NASA is pretty much behind every conspiracy ever. Okay. I learned that on August 27th of this year, the planet Mars is going to be as large as a basketball in the sky. And, I'm a little skeptical about these things, but that's because I'm a Libra. So let us start talking about astronomical myths, misconceptions, and illusions. Okay. The first one we start off with is that famous Mars illusion. Mars is going to be as big as the moon in the sky. Well, this actually has a pretty interesting origin. It originates back several years ago when Mars was actually a little bit bigger than it was in the sky. A little bit bigger at its opposition than it normally appears. Someone passed around this note, which actually makes a lot of sense. There's a lot of things that this person writes. He says that Mars is going to be 25.11 arc seconds wide, which is very, very tiny in the sky, requires a telescope. He also says that at a modest 75 power magnification, Mars will look as large as the full moon to the naked eye. Now, okay, so this is an interesting example of evolution, okay, in action. So, over the next couple of weeks, this particular email got passed around by millions and millions of people, and it evolved very slightly. So here's the key critical element. And it slowly morphed into Mars will look as large as the full moon to the naked eye. They dropped that in the 75 power telescope. This got passed around and it alarmed a lot of people. Now, I don't know about you, but about every year at about mid-August, I start to get this email again, and it says it's going to happen on August 27th, and people seem to have forgotten that it happened every single year before that. Well, let me tell you what really happened here. Okay. So back in 2003, Mars went through what was called opposition, which means that it was on the opposite side of the sun from the Earth. Mars has a slightly elliptical orbit, as Kepler discovered. And some of the time, Mars is a little bit further away from the sun, and at other times, it's a little bit closer to the sun. And at this point in its cycle of oppositions, it happened to go through opposition at a point that was very, very close to what's known as the perihelion. And that's the closest point that Mars reaches in its orbit, the closest point that a planet reaches in its orbit. It was right there, 34.6 million miles away. And that's pretty cool, because it was the closest it had been in something like 50,000 years. And this was a really astonishing opposition at the time. But it wasn't going to make Earth or the planet Mars, look as big as the moon to the naked eye. So, what we've got is moon, Mars, no. Yes. Not quite as exciting. Not quite as exciting, but the truth. So I want to go through a little test for you to kind of get you ready for the next segment. Let's first start off with a question, and you guys can just shout it out. Who created the theory of relativity?
Albert Einstein.
Albert Einstein. There you go. Albert Einstein. Who created the third law of motion?
Isaac Newton.
Isaac Newton. Yes, you are correct. Who invented the telescope?
Some Dutch guy.
Okay, I heard a couple of Galileos. Okay, but some Dutch guy. Some Dutch guy. I'll just wait here while you guys think about it. Okay. It was actually a guy named Lippershey. Okay, probably. Okay, so, but what I did there is a couple of you guys, I heard a number of people saying, "Oh, it was Galileo," you know, and even if you hadn't, you had known that it was some Dutch guy, as Jason said, and not actually Galileo. I had actually done something to you psychologically that made you think ahead of time that that maybe it would be actually Galileo. I did something called priming, and this is a psychological trick where you get someone in the habit of thinking in a certain way. And so Galileo, Newton, Einstein are very often featured together in articles like this, or when you talk about Einstein and Newton, Galileo is often thrown into the mix. So what I did was I made you want to say Galileo in a way, and this has actually happened in a case of Percival Lowell, and I kind of want to tell you that Percival Lowell was not actually as crazy as we seem to think. Now, the story of Percival Lowell is that he heard a guy named Schiaparelli, who was from Italy, and he learned that Schiaparelli had seen these little lines across the face of Mars, and he called them canali, which in Italian basically means channels. And so Percival Lowell decided, no, I really want to go out and see these for myself. And he promptly looked at Mars, primed with the knowledge that there were canals on Mars, and he himself saw canals. But I also want to say that maybe he was actually seeing something. I want to do a little experiment for you here. Let's turn off my flashlight before my phone dies. Okay, so here's a picture of a square, and basically what I did was I took a small square and a large square of two different colors, and then I blended them together. Now, you guys probably can see from where you're standing these little lines right here. Do you see these little lines right there? Mm-hmm. Those little lines are not really there. Okay, so let's take a look. So here's two of them side by side. Now, I'm going to cover up one of these, but for a tiny little portion. Now watch those lines disappear. Okay, so I've covered up most of it. I didn't do. You have to take my word for it, but I didn't do anything to that gray line. Notice how those little lines disappear. This is something called the erratically effect. When you have a continuum of color that goes from one color to another, you can actually get these little psychological lines that appear to the eye. Let's do a little movie here. I have my little movie. Okay, I have to bring up my click there. Let's see if I can actually demonstrate the erratically effect. See how the lines seem to disappear as we cover up the square there. And the Early effect doesn't just occur in squares. It actually can occur in any sort of shape. So what I did here was I took a bunch of blotches and then I just created smooth gradients from the edges of these blotches and made slow, smooth gradients. It's actually a lot clearer on my computer screen here, so maybe afterward I'll show you. But you guys can see lines along these things here. These lines aren't really there. If we were to cover up those blotches and just, put a line right across there, that line wouldn't exist. It's a purely psychological phenomenon. So Percival Lowell may have actually been seeing, because of the differences in color on the surface of Mars, these lines. So he might not have been totally, as they say now, cray-cray. Let's move on to another illusion that's a little bit more noted in our current day and age. I grew up reading I'm going to turn this down just a little bit. There we go. Okay. I read the Burnham Celestial Handbook, and I read a lot of old astronomy magazines. And if you read like Walter Scott Houston and that kind of thing, one of the things that they talked about a lot when they looked at things like globular clusters or open clusters were these little trails of stars and places where the stars were not. And this is an article in the Burnham Celestial Handbook about M13, and he says, the most prominent of these dark blots may be seen in the photograph on page 985 near the right edge of the central mass. There also appear to be several ill-defined dark lanes at various positions in the cluster. 3 of these meet in the southeast side of the central core to form a Y-shaped pattern, which was noted by Lord Rosse more than a century ago, which is very evident in medium-sized telescopes today. So basically what he's saying is, I'm seeing these dark blobs on the face of M13, and these trails of stars that occur on the face of M13. Now the thing is, they're not really there. And I'm going to show you why they appear. Okay, so let's take a look at a picture of M13 taken by one of our noted astrophotographers who is sitting in this room.
That is awesome.
Okay. Now, if you look at it closely, you can actually start to see, this actually doesn't really show the lines that you see in the telescope, but, if you stare at it a while, you can actually see, there's a little bit of, there's something there, maybe that's a line there, maybe that's a line there. This is actually a phenomenon of simple randomness, basically. If you take a random set of dots, which I've done here, this is just a random set of dots, and you look at it closely, you can actually start to see patterns in it. Now take a look at it. I'm seeing these little blobs here. If we were looking at a star field, we might expect that star field actually has some intervening gas and dust, blocking out the stars. But really what it is, it's just the effect of the fact that stars are distributed randomly. So we've got that. Maybe we've got a little line there, a little bit. Oh, look at that line. That's a really clear line. You guys see some lines in there? So let's see. Okay, yeah, I'm seeing quite a few of them. And I've done something that looks a little bit more like a globular cluster. I've done the random dots, but I've caused a gradient across them. And here you get lots of lines. There's, Corona Borealis or something like that. Okay, and you've got some blots up there. There's a little Bach globule, as they call them, a big cloud of gas and dust that occurs in that globular cluster. There is no cloud in front of M13. If you look at it in infrared and you look for the cloud, there is nothing. It is purely an illusion. This is something that has confounded amateur astronomers for years, showing that even if you're an experienced observer like Burnham or Walter Scott Houston or one of us, that you can see these things. So you can be fooled. So speaking of alignments and things lining up, I want to talk about another form of alignment that often gets passed around in social media, and that's the alignments in the sky. I want to tell you that they're not really all that surprising. But a lot of people seem to think that something like this is going to happen when you get Jupiter and Saturn and Mars lining up in the sky. So how does this, happen? Why, what's the process by which this goes about? So I'm going to give you a little movie here to demonstrate kind of what you might expect to occur when the planets line up here. So I will click on my my movie here and demonstrate. Okay, oh, yeah, not to scale, just to let you know. Okay. So this is the hypothetical model for what the planets destroying the Earth. So let's take a look here. So they're going around at random, not to scale. Okay. Oh, and they're lining up. Okay. Yes. So. Okay, so that's the theoretical model as to what's going to happen. So I tried to come up with some sort of explanation for why this is happening, and barring any unknown physical force that exists in the universe, I would say that the most plausible explanation for making the Earth do this is gravity and the tides. So that's the most plausible force. It operates over a very long distance, and it's the force that holds the solar system together. So let's take a look at a worst case scenario and see if this model of the universe is actually a plausible model. So what I did was I took, first of all, and I looked at the solar system from the edge on. We left out Pluto here. And a lot of this comes from the fact that when things line up in the sky, people consider that to be very significant. Well, actually, it's not all that significant if you take into consideration the fact that everything is actually orbiting in the same path. In fact, it's about as significant as cars lining up on the freeway, because they're all traveling along in the same path. So you end up getting something like this, and many of you Carl Sagan fans will notice this little movie. We'll notice this little movie. So the planets actually travel through a very narrow band in the sky. And if you watch the traces, they seem to follow a very narrow path. And they go through what's called the zodiac, which are the 12 constellations that circle the sky and which the sun appears to go through. The trail that the sun appears to go through is what's known as the ecliptic, and they trail more or less that path in the sky that's fairly narrow. And so alignments, given the fact that they're all traveling along the same freeway, are to be expected. So it's not really the fact that they're lining up. So let's take a look at what else might it be. Well, maybe it has to do with them being all bunched close together on one side of the planet. So what I did was I took the worst case scenario and put them in, took the worst case scenario of all of the planets and put them into an Excel spreadsheet here, figured out how close the planets could get, added it all up, and compared the tides of all of the planets combined to that of the moon and the sun together, or just the moon. Now the tides actually vary according to a very simple equation. This is probably the scariest thing I'll have in this talk, which is a tiny bit of math. As you get further away, the tides decrease to the third power. So if you double the distance of two objects, the tides actually decrease by a factor of 8. So they're 1/8 the force when you double the distance. If you triple the distance, it's 1/27th. You know, it actually goes down. Well, if you add up the force of all the planets in the solar system, throw in Pluto into the mix, it turns out that the tides of the moon are 17,300 times greater than that of all of the other planets combined. So I don't think we're in any danger, even in a worst case scenario, unless there's some sort of woo-woo rays out there that are going to cause the Earth to be destroyed. So we don't have to worry about that. So you can safely ignore the portents of doom and gloom. Okay, so here's another illusion that people often fall for. This one's called the moon illusion, the full moon illusion. Let's take a look. I even spelled it in the politically appropriate way. Okay, so once a month, we've got a lovely full moon rising, and darn it, if I can't help myself from seeing it as being really, really large in the sky. And a lot of people think, of an astronomical bent, think that maybe that this is some trick of optics. Maybe the atmosphere is magnifying the full moon. Maybe maybe the moon is just a little bit closer at that point in its orbit. Neither one of those things are the case. In fact, it's actually quite interesting. Even though you've got, so this is something that, this is kind of the model that people have for it. They think that the moon is actually appearing larger because it's close to the horizon and the air is somehow magnifying. And I've seen this as an explanation for why the moon appears big. If you actually took a photograph of the moon at the horizon and then took a photograph of the same full moon up at the zenith, they'd appear pretty much the same size with one exception. You've got something interesting happening here. When the moon sets, or the sun sets below the horizon, the atmosphere actually pulls the moon up a little bit above the horizon. So when you see, for example, the moon set or the moon rising right at the horizon, it's actually a little bit below the horizon. The atmosphere acts as a prism, pulling it up. Well, the further below the horizon the moon actually appears, the more the lift is. And what ends up happening is you get a little bit more lift on the bottom of the moon or the sun, and a little less lift on the top of the sun, and you end up with something like this, where the sun is actually a little bit squished, or the moon is actually a little bit squished. So if you watch the sunrise or the moonrise, at certain times, if the conditions are just right, the sun actually appears to be a little bit squished from top to bottom. So not only is the moon not bigger in the sky because of some optical effect, it's actually smaller in the sky from top to bottom because of some optical effect, because the bottom is getting lifted up a little bit more than the top. But why do we see it this way? Well, let's take a look here. Say a high-tech Photoshop picture that I created myself. Okay. So which dog is bigger? Anybody want to take a guess?
Neither.
Okay,
Both
yes.
dogs are saying
Okay.
in line.
Which dog looks bigger?
Top.
The top one. And it's very hard. I mean, you guys are skeptical astronomers. You guys know the game. So obviously these dogs are exactly the same size, but darn it if you can't see the top dog looking a lot bigger than the bottom dog. So let's take another little view and replace the dog with the moon, and I will prove to you that the moon at the bottom is the same size as the moon at the top, even though the one at the bottom looks quite a bit smaller. So let's do our little thing here, and we'll move it up, and it appears to get bigger and bigger. So they are the same size. They really, really are the same size. So this is called what's known as the railroad illusion. If you grew up looking at optical illusion books like I did when I was a kid, you would see this type of thing in optical illusion books all the time. It's a good trick to play. But I think that the opposite of this is what is happening when you have the moon above the horizon, like this, you end up with, let's try to start that movie, it's not starting. When the moon is high up, it actually looks very small, but as it moves down toward the horizon and you've got your perspective from the road, hello, go. This is, there we go, okay, so. And as it moves down to the horizon there, it starts to look bigger and bigger. And it's very hard to convince your brain that that is not actually bigger than it was up here. This one, even if you're just looking at it in a photograph like that, certainly looks a lot bigger to me when you're looking at it down there at the horizon. So the railroad effect is probably one of the best explanations we have for why the moon illusion occurs. We seem to think that things that are close to the apex of our perspective are bigger than the things up there at the top. It's just a weird way that our brain works. So, okay, here's another one that amateur astronomers are subject to. I've got my little technological music here to go with this. A lot of people imagine getting a bigger and bigger telescope. I have an 18-inch telescope, which I got specifically to make objects bigger and bigger and brighter and brighter. Well, it's commonly thought that one of the reasons why you own a telescope is to make things actually brighter, when in fact, telescopes do not increase the surface brightness of an object. And I'm going to use a little bit of math to explain why that is. You'll never actually get a telescope that will show you the sky so brightly that you will see it like the photograph on the box of the telescope. It won't actually happen. So let's take a look here. So you're never going to get, imagine you've got an 8,000-inch telescope. This is not what you're going to see. And the reason why that is because you cannot make things in the sky with a telescope brighter than they appear to the naked eye. You can make them bigger than they appear to the naked eye. And you can keep them roughly at the same brightness, but you cannot make them so bright that you'll see this amazing amount of detail, which is kind of disappointing. You need a camera to do it. But let's take a look at what happens. Now, there is actually an exception to this. It's kind of an interesting side note. Stanley Kubrick, when he made this movie, does anybody know that movie? Barry Lyndon, yes, I heard that. Okay, so Barry Lyndon, he decided that he wanted to actually make a telescope back in the film days, in 1975, and he wanted to light this film in the same way that people in the 18th century would be lighting their setting, and purely by candlelight. So he needed some camera lenses that were exceptionally powerful. They gave a lot of that actually captured all the light that was there that he could get. So he had heard about this NASA camera lens that had been developed that had an f-stop of 0.7. That's actually less than f1. And this is generally, in terms of telescope, this is not possible. You can't make a Newtonian telescope shorter than f1. But this had a curved back, and then when the film went into the camera, the film was bent in order to receive the light, and by doing this weird effect, he was able to get this 0.7 f-stop. Now, this would not be good for a telescope because of what I'm going to tell you. Where this brightness. If you were to double the magnification, you're taking all the light that was in this square and stretching it out and stretching it out over these four squares. So you're doubling the magnification by making this side twice as long, this side twice as long. So you're actually taking all this light, spreading it out. If you were to magnify it 3 times, you would actually spread out the light over an area that's 9 times as large. So the brightness of this square is 1/9 the brightness of this square when you magnify it 3 times. So when you actually take something with a telescope and you magnify it, you're stretching the light out and making it dimmer. So, but telescopes actually gather more light than our eyes. So why can't we get a telescope that actually creates things that are brighter to the eye than what we see with the naked eye? So you guys probably, many of you have binoculars. The binoculars have this little thing on the side, 7 by 50. What is that all about? 7, the first number represents the magnification, and the second number represents the aperture of the telescope. And there's a very simple formula for figuring out how much light you can cram into an eyepiece. And it's called figuring out the exit pupil. And the math is the simplest math you could possibly imagine. The size of the little cone of light that comes out of a telescope eyepiece, or the eyepiece from a pair of binoculars, is only the aperture divided by the magnification. So let's do that for these binoculars. Okay, the binoculars are 50 millimeters across, and we divide it by 7, and we get 7.2 is the result. So the binoculars were pretty well designed because, on average, the human eye at night, the pupil opens up to about 7 millimeters if you happen to be young and sprightly. If you get older, it gets a little smaller. But so this is actually a good, a good indication of what your best possible scenario for gathering light is with your eye. If the magnification or the exit pupil fits perfectly in your eye. If the magnification were actually a little bit lower, like 6 here, or maybe we'll put it at 5, 50 millimeters, the exit pupil would be 10 millimeters in size, and since our pupil is only 7 millimeters across, some of the light that was actually coming out of that little eyepiece would be lost, and the object would not appear brighter to us. So let's do a little bit more math. Okay, so we've got our binoculars here at the top. If you have low power, you get a large exit pupil that can just barely fit into your eye. You crank up the power, you get high power, that exit pupil gets a little bit tinier. So how does this work in practice? If you take an 18-inch telescope, which is near and dear to my heart, about the lowest power you can get and still have a 7 millimeter exit pupil is about 65 power. So that is actually the best possible scenario you can have, because the image is smaller, brighter, the background is brighter. You actually have the smallest possible image that you could get. If you were to blow up to 4 times that power, you blow up the image, you actually have 1/16 of the light per unit area in the sky. The galaxy is much, much bigger, but it's also much, much more spread out at the same time. So you're not getting any more. You're not getting any more brightness. You're not getting that photograph on the box appearance by actually spreading out the light. The best possible scenario is the thing that is right at your smallest magnification. So let's compare 2 telescopes here. An 8-inch telescope will give you an exit pupil of 7 millimeters down at 29 power. An 18-inch, as we learned, was 65 power. So what's the difference between an 8-inch and an 18-inch? Well, with an 8-inch, you get something that is equally bright as an 18-inch. The sky is the same brightness, the object is brighter. But with the 18-inch, you actually get a bigger view. So the image is actually larger and the same brightness at the lowest possible power of the telescope. So this gives you the ability. So what a larger telescope does is it gives you the ability to see something at a higher power at the same brightness. So let's go through a quick little, I'm sorry to inflict a little math on you. Let's make a little comparison. If you have an 8-inch mirror, that's 203 millimeters for you guys, and a human eye, which is 7 millimeters across. And let's simplify things by making them into a square, because it's easier. You don't have to have pi in the mix. If you take 203 millimeters and you square it, we have 41,209 square millimeters, and the human eye, our square pupil, we have 49 millimeters. So what's the ratio of the amount of light that the telescope is gathering to the amount of light that our eye is gathering when you have an 8-inch telescope? Well, the ratio, if you divide that 41,000 by 49, you get 841. So you're actually gathering 841 times more light with your 8-inch telescope than you are with your eye. So you're cramming all that light, you're cramming 841 times more light into your eye. However, at the same time, you're magnifying the image. And this is kind of where it gets a little confusing. So let's take a look. We can get for 7 millimeters, we can get a magnification of 29. Our magnification of the human eye is 1. Okay. If we spread something out by a factor of 29 in every direction, we get 841. So the amount that object is being spread out is over an area 841 times as big. So you're taking the same amount of light, spreading it out over an area that's 841 times as big, but notice that these are exactly the same. You're actually getting, at the lowest possible power that your eye can, the light can actually fit into your eye, you're getting the same light ratio in both situations. So the image does not actually get brighter. It only gets 29 times bigger in the view. Now, this doesn't take into consideration the fact that with a telescope you have some light loss going through the lens, so you lose a little bit of light there, and then you have the secondary mirror, which is actually blotting out a little bit of the light and that kind of thing. So you cannot get an image that is brighter than is in the night sky with your eye. You can only get as bright. You can just make it bigger. Yes, Don?
With one exception to that, stars.
Stars, yeah, that's true. A star, yeah, that's true. A star can be made bigger, and the problem with that is, the thing about stars is they're point sources. They don't actually get spread out. This is only for extended sources. That's true. So you're never going to get. I have actually looked through a telescope that's 120 inches across. I had a wonderful opportunity to do that, and this is not what you see. You basically see that little fuzzy blob a lot bigger. And it's bright and it actually looks nice. You can see a lot of detail in it because it's bigger. But you don't get colors and that kind of thing. There is no hypothetical telescope that will give you this view, which is very sad, but that's what happened. That's the way things are. So, the last thing I want to talk about is some pretty interesting optical illusions that are hard to not see, even if you are an experienced and skeptical amateur like myself. So that star is following me. So let's take a look. Pick a star and watch it. Just stare at it while this movie is moving. Now gradually, you'll start to stop seeing the trees moving so much, and it will seem like the stars are slowly starting to push forward. Does anybody see this illusion? The stars will start to be pushing a little bit to the my left, your right. Okay. So now watch what happens when the video stops. It'll actually make it appear like the star lurches backward. 45-second video. It's quite a long time. Okay. So it kind of comes back. Your eye actually adapts to the motion of the background, and the star appears like it's moving backward.
It's still moving backward.
It still feels like it's moving backward. It's not moving, I guarantee it. That's only in your head. But you guys are skeptical. You guys know that it's not moving, but it's hard not to see it. Now this is a trick that happens a lot. I've seen people think that bright stars that are high up at the zenith are actually moving. I'm going to do the same thing with clouds. And it really happens with the clouds because you kind of glom onto them. And I've had people say, oh yeah, that star is moving. Or I've looked up and I've seen Regulus or something like that behind the clouds. And it appears like it's moving. I mean, I think, oh, it's a satellite. No, it's just Regulus, and I'm locking onto the clouds. It's a pretty cool trick. Now, when it stops, you'll see it's moving up. I can even see it from the side. Okay, now things get really weird when you get two layers of clouds going at the same time. So what ends up happening is you alternately lock onto one layer of clouds and then another layer of clouds. And what ends up happening is the star seems to kind of move a little bit like this. Sort of, it kind of wobbles around a little bit. And so, can you guys all see that illusion there? Yeah. So, I've had people convinced that have come up to me in programs here at Perkins that are convinced that that star right there is going around in a zigzag, moving around and that kind of thing. No, it's not doing that. You're looking at the clouds. And there are some other things that can actually affect this. At nighttime, we can get a little tired. Our ability to judge our own balance changes when the light levels get very, very low. And this affects what's called our vestibular system, the relationship of our sense of orientation to the organ in our ear that actually gives us direction. When that gets messed up a little bit, we can get a little bit disoriented and actually see things moving. I'm sure that a number of you have indulged in some legal substances at some time and woken up in the morning and felt your vestibular system going all kind of crazy. The floor is tilted and that kind of thing. This happens at night when you're tired and your glucose levels are low and that kind of thing. So even if you are a dyed-in-the-wool skeptical astronomer, you don't believe any of this woo or any, this star, this is not an alien spacecraft that is following you, it's still possible to actually see these illusions. So what to do with this? Well, I want to ask you to do the following. First of all, know your own limitations. Know the fact that your brain plays tricks on you. These illusions are proof of that. You can get seriously wrapped up in thinking that something is happening that's not really happening. But if you're aware of the fact that these illusions do in fact occur, you can get over it. Second of all, don't take social media as gospel. Social media is not a good source for astronomical information in general, unless it comes from one of the esteemed members of the Columbus Astronomical Society. And third of all, be sure to wear your tinfoil hat. So thank you very much. Okay, so anyway. Yes, questions?
Well, I see there's this pan on the other side of the stopping line. Of course, the government's keeping how much away from us. You know what I'm talking about? There's another planet on the opposite side of the sun that we can't see.
Oh, how do we know that doesn't occur? Well, first of all, spacecraft have left the Earth and taken photographs of the solar system from a distance. We have the SOHO spacecraft, which are now on the other side of the sun. There just so happens not to be another a planet on the other side of the sun.
There's also a really cool Voyager 1 picture, family portrait of the solar system.
Yeah, I mean, first, and second of all, it would also mean it would not be particularly stable. Gravitationally, that would not actually be particularly a good orientation or configuration. So, anyway.
Let's leave the facts out. That's okay.
Yeah. So anyway,
Now, why are you saying that NASA says behind every conspiracy?
Oh, because it is. Yeah, I don't really mean that. So, yeah, that's a joke. Yeah.
The squishing of the, like the sun, you know, at the horizon, when you see it like squished like that.
Yes.
Is that because the atmosphere is denser closer to Earth and less dense farther?
Correct. When the bottom of the sun is actually going through more air, and the air is actually denser at the bottom, closer to the horizon. The further up you go, the less air you look through. You're actually looking through, you look straight up, you're looking through one atmosphere of air. You look almost horizontally, you're looking through 15 atmospheres of air. You're actually looking through the same amount of air multiplied by 15 horizontally. But as you go up, it drops down dramatically. When light goes through a denser, passes from a less dense to a more dense part of the atmosphere, the refractive index, the amount that light is bent, is greater the closer to the horizon that you go, and so the more the light is actually bent upward. So as the sun comes up, you'll actually, if you see these movies, sometimes what'll happen is the sun will come up and it'll be sort of this flattened orange shape, and then as it goes up, it'll slowly round out as it rises. Yes.
Right. Yeah, just to clarify, Brad.
Yes.
The sun and moon suspend a half a degree.
Yeah.
And by the time when they appear to us to hit the horizon, they are already below the horizon.
Yeah, they're already well below the horizon.
Below the horizon.
Yeah, it's something like 1.5 degrees below the horizon. It's a pretty big distance. So yeah, but when you see the sunset, that's not the geometric sunset. It is actually below the horizon a little bit. So yes.
Is that also why we're able to look at the sunset with our eyes as opposed
Well,
to...
you shouldn't be.
Generally, it's not a good idea to stare at the sun at any point because it's pretty bright. The best time to look at the sun, if you want to look at the sun, and I didn't say this, is at sunset because you're actually the atmosphere is filtering and scattering out the most amount of ultraviolet light at that point. But still, I wouldn't recommend it. Chinese astronomers actually noted sunspots well before Galileo noted sunspots by looking at the sun actually setting very, very close to the horizon. If there's a lot of smoke in the air and that kind of thing, you can actually see some of the largest sunspots. Yes?
What's the name of that thing again? That phenomenon where you see lines because of radiation?
It's called the Yarely effect.
How do you spell that? Yarely.
Yarelley. Okay, so yeah, it's the Yarely effect, and it's a really cool. I love this illusion. I mean, it's a fantastic. And all I did to make this little square, and I don't know how easy it is to see from down here. Yeah, it's pretty good. Okay, so from this angle, we get a lot of glare off the screen. But these lines aren't here. All I did was I took a square, took another square, and then I blended them in Adobe Illustrator. And these lines just naturally show up. It's just an optical illusion. So, yeah.
I think we had I'm sorry, this is more similar to your moving star illusion, but I remember one time we saw a geosynchronous satellite, and it was in a scope that wasn't tracking the stars.
Right.
And it looked like that one
star was moving.
One star was moving against the star field. It was really the star field that was...
Yeah, the star appears to be... Okay, so he's talking about a situation... if you observe the wild duck cluster, M11, which is for Ohio's latitude is just about right at the right point. A couple times a night, a satellite will pass through the wild duck cluster. It's just, if you go to Greaser Field, let me think.
It usually only occurs in April.
Yeah, okay. So what we've got is there are a number of geosynchronous satellites. Geosynchronous basically means it stays in the same part of the sky. So if I pointed in that direction right now, I might be pointing at a satellite, 7 hours from now, I could still point in that direction, and that satellite would still be in that direction, in that spot. And what happens is, it follows the satellite actually follows the Earth as it turns around. Now, the stars move behind the satellite, but the satellite remains in the same place. So if you happen to get one of these in your telescope, a really good way of doing this is to look at M11, which is a beautiful star cluster. It's worth a look by itself. But every once in a while, there'll appear to be a star that will move through M11. I've seen it a number of times at Perkins. If the telescope you're using is not tracking the movement of the stars, if it's just a Dobsonian telescope, doesn't have any motor on it, that star will be fixed in one spot, whereas where the geosynchronous satellite will be fixed in one spot, whereas the stars will actually be moving through the field of view. But it's very, very hard to see the stars as moving, and that little satellite is not moving. What it will appear to be, it'll appear that the geosynchronous satellite is actually moving through the field of view, but never leaving the field of view. It'll always appear to be moving forward, as the stars slowly move out of the field of view. And it's a really interesting illusion. I've experienced it a number of times. So, sorry, it took a long time to explain. Yes?
Okay. On the sunrise and sunset times,
yes,
you're saying that, this effect of the sun actually, or in this case the sun, actually being below the horizon.
Yeah.
Okay. So then, at what exact point then is the sunrise and sunset? At what point is the sun, when does the sun actually going to rise and set?
So what's the geometric sunrise and sunset?
Well, you get the disk of the sun.
Yeah.
Okay, then at what point exactly is that sun then going to rise at, say, let's say 6:30 in the morning?
Yeah.
So at what point?
The definition of sunrise.
Yeah, what's the definition of sunrise?
Or the trigger?
Okay, yeah, okay, so the published sunrises that you see are actually the visual sunrises. It's not the geometric sunrise. It's not the point at which the sun appears to, if you had a hypothetical, atmosphereless Earth, at what point the sun would appear to pop up over the horizon. It's actually reported in such a way that it's when the sun appears to pop over the horizon. That's generally what they report. And that can vary by a few seconds, in either direction, depending on the density of the atmosphere.
So is it the leading edge?
It's the leading edge. It depends on the source. Most of the time it's the leading edge that pops up. But sometimes they go for the middle of the sun.
Oh,
but if you look at the reports, for example, if you look at the reports of the sunrise and sunset on the equinox, it actually turns out that the daytime is a little bit longer than the nighttime. And the reason why that is because on both the sunset and the sunrise reporting, the sun has actually risen up a little bit on both ends. And so you have a longer day than at the equinox than you have night. When actually, geometrically, the sun should be taking the same amount of time to go below the Earth and above the Earth, from our point of view. If you take a look at the report of the sunrise and sunset at the equinox, there's a couple minute difference. It's actually a little bit toward the day being a little bit longer. So, yeah.
Brad, when the moon's just coming up on the horizon, it looks really big.
Yeah.
Have you ever stretched your arm out and put the tip of your index finger by the moon,
Yeah.
and it'll be about half the width of the tip of your index finger.
Yeah.
You wait till later on in the night when the moon's higher, it will look smaller. But if you do the same thing,
Yeah.
the moon will still be about half the width of the tip of your index.
Yeah, if you use some sort of ruler or something like that, some sort of device that measures the size of the sun, take a photograph of it or what have you, the moon will look half a degree wide at the horizon, half a degree wide up in the sky. And so, yeah, your pinky will be a good reference.
It's a fun thing to do at night.
Yeah, it is.
I was going to add one thing. Actually, the interesting thing is, when the moon's near the horizon, you're actually about 4,000 miles further away from the moon
Yeah.
than you are when it's at zenith. So it'd actually be a
little bit smaller.
bigger at zenith than it is at the horizon.
Yeah, a little tiny bit bigger because of the tilt of the Earth. So, you know, when the moon is straight overhead, half of the width of the Earth, you're half of the width of the Earth closer. The thing is, though, that doesn't really come into play all that much because it's subsumed almost entirely by the fact that the moon's orbit is not, not a perfect circle. Sometimes it's closer, sometimes it's further away. And it's very difficult to see the difference between a supermoon, which they call, and a normal run-of-the-mill moon. And supermoon doesn't look bigger to our eye because we're not able to judge those distances. So it's entirely a railroad effect. So anyway, thanks guys for listening to my talk. It's very short.
I don't suppose it's clear outside, but we can check.